All right, in this video, we're going to take a look at finding combinations of objects. So in our last video, we looked at permutations. In this video, we're going to look at combinations. And the ideas are very similar, but there is a distinct difference. In fact, the difference also is in the formula for combinations itself. So with permutations, order selection mattered, so that if we have ABC, ACB, BAC, BCA, CAB, and CBA, these are all considered different. So let's say A, B, and C represent runners in a race. So each one of these values is a different outcome for the race, and in this case, the order would matter. However, with combinations, in the eyes of combinations, selection order does not matter. So there's no distinction among the orderings above. So in combinations eyes, ABC, ACB, all six of these orderings are all the same. It doesn't matter what order you place, just as long as you place, if you want to look at it that way. So notice that there are 6 or 3 factorial arrangements of those letters A, B, and C, in this case with combinations. And that is actually going to help us develop the formula for finding the number of combinations of n items taken r at a time. And we're going to use the permutation formula and then have this this particular value here, but we'll generalize it to distinguish between combinations and permutations. So example 7, 5 people are competing for 3 equal prizes. How many ways can the prizes be awarded? So this time, instead of having like $1,000, a $500, and a $100, let's say each of the 3 contestants who win get $1,000. So it doesn't matter if you came in first, second, or third. As long as you got in the top 3, you're going home with $1,000. So if order mattered, like it did in the last video, if order mattered, then there would be 60 different possibilities. So again, ABC, BAC, yada, yada, yada. Now with combinations, this ABC, this BAC, and this ACB, and this BCA, these are all the same. So combinations, they don't see a difference in combinations between ABC, BAC, ACB, BCA, etc. It's using the same 3 letters where the order doesn't matter. So since ABC is the same as those other ones in the eyes of combinations, we can take our permutation result of 60 and divide it by 3 factorial to get 10 combinations. So we want to get rid of all these ones that through combinations mean the exact same thing. And we know that with 3 letters, taking 3 of them at a time, there's 6 different ways we can order those 3 different letters. So 3 factorial is 6. So if we take the total number of permutations, which was 60, and divide it by that 6, we get 10 combinations, which I've listed right here. So with combinations, ABC is, as long as you're in this group, you would have won that prize, or A, B, and D, or B, C, and E, you would have won that prize. So here we have 10 combinations of 3 letters that we took out of a list of 5. So if we have n items available and we take r at a time, this time without regard to order of selection, then the total number of possible combinations are n factorial over r factorial times, in parentheses, n minus r factorial. So it's the permutation formula dividing the permutation formula by r factorial, which in our last example we divided it by 3 factorial because we were taking 3 of them at a time. Dividing by r factorial, we can just put that in the denominator of our fraction. And here is our formula for combinations, which you might also see written in this form with these tall parentheses. So either using the NCR, which I'll stick with NCR, I believe, in this video, or it's oftentimes written this way as well. So with combinations, this just like we looked at awarding equal prizes, it doesn't matter what order you finish, as long as you finished in the group that gets a prize. Combinations, if it says combinations, but not the combination lock. I know it's it's not a very good choice of words to name it a combination lock. They should name it a permutation lock, because if we dial the combination in a different order, we hopefully don't open the lock. Or committees where there's no like assigned positions. Really, you're just on maybe a 4-person committee that discusses whatever. So example 8, a committee of 5 is to be formed from a pool of 12 potential candidates. How many committees are possible? So here we have committees, and I always remember the committees combinations. They have the same 3 letters, at the beginning. So we have 12 candidates to choose from, and we're taking 5 at a time. And if you ever goof up and mix up the order, your calculator might give you a 0 as an answer or an error message. So if it does, then try switching the numbers and hopefully it'll work. So 12 factorial over 5 factorial times 12 minus 5 factorial gives us 792. Now, if we want to look at Desmos, if we go under functions and stats, this time NCR, and we could type in 12 for our value of n and 5 for our value of r, and we get our 792 again. So we get the same answer. So most calculators have the ability to analyze factorial, permutations, and combinations. All right, example 9, a committee of 5 is to be formed from a pool of 12 candidates. This time, the committee is to be made up of 3 managers and 2 accountants. So we want to make sure we have specific roles on this committee. If there are 8 managers and 4 accountants available, how many committees can be formed? So we need to make sure that 3 of the positions on this committee are managers and that 2 of the positions on this committee are accountants. So we need to blend using our fundamental counting rule to get the total number here along with combinations. So we need to find out how many ways are there of selecting 3 managers from 8. That's a combination. And then we're going to multiply that, and that's our fundamental counting rule. We're going to multiply that by how many different ways are there of selecting 2 accountants from a group of 4. So in this case, picking 3 managers from 8, we have 8C3, and then for 2 accountants from 4, we have 4C2. And we can calculate these individually. 8C3 is just 56. 4C2 is 6. So there's 56 ways of selecting 3 managers, and we have 6 ways of selecting 2 accountants. So our fundamental counting rule says multiply 56 times 6, and we get 336 ways that we can make this committee so that there's 3 managers and 2 accountants. All right, example 10, starting at point A and moving only right or up. How many paths are there to get to point B? So you have to go to the right a total of 5 times. 1, 2, 3, 4, 5, and then you have to go up a total of 1, 2, 3, 4. There's one possible path, 5 rights and 4 ups. Another example would be 2 ups, a right, an up, 3 rights, an up, and a right. So notice we're making U's and R's for ups and rights. And out of the 9 letters available, 9 letters, which are the total number of spaces we have to walk, out of these 9 letters, we need 5 R's and we need 4 U's. So this can be, again, solved using the fundamental counting rule and combinations. So we need to pick 5 R's from the 9, and then out of the remaining 4 letters, we need to pick 4 of them as U's. So picking 5 R's from a group of 9 letters is 9C5, where, again, the order does not matter. If you go right and up, it's the same as going. You're going to end up in the same spot as up and right. And then picking 4 U's from the remaining 4 letters is 4C4, which 9C5 is 126, 4C4 is 1. So we have 126 different routes we can take from A to B if we can only go right and up to get there. All right, 11. How many ways can 20 people on the youth center basketball team be grouped into 6 centers, 4 shooting guards, 3 small forwards, 2 power forwards, and 5 point guards? How many ways can we assign the positions that way? So let's start with the centers. We have 20 people available, and we want to take 6 of them to be centers just to have a nice healthy mix so the kids can play, get some court time. So we have 20, and we're choosing 6 of them, so 20C6 as the number of ways to select the centers. Then the shooting guards, we've taken 6 of those players out as to make them centers, so we have 14 players left now in the pool of candidates, and then 4 of them we're going to pick to be shooting guards, so 14C4 for the shooting guard position. Small forward, we've taken 4 of those players out of the out of the pool of candidates. So we have 10 players left. 3 of them we want to play small forward, so we have 10C3. Now we have 7 players left after we've taken out the 3 small forwards. And out of those 7 players, we want to assign 2 of them power forward, so 7C2. And then we have 5 people left for 5 positions, 5C5. So we're just going to multiply each one of these values, and we get about 97.8 billion different possible lineups that we can make, or different ways we can do this. So quite a few. Now there is an alternative approach to that last problem. So if you don't want to multiply out all these combinations, there is a quicker method. It involves, I think it's called the partitioning method. And that's by taking n factorial over r1 factorial times r2 factorial times r3 factorial, yada, 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 times rk factorial, where r1 plus r2 plus r3 plus all the rk values in the denominator, that total has to equal n. So in our last example, we had n is 20, so 20 factorial, over, I believe we had 6 centers, 6 of the centers, plus 4, plus 3, plus 2, plus 5. We add those 6, 4, 3, 2, and 5. They do add up to 20. And we could take 6 factorial times 4 factorial times 3 factorial times 2 factorial times 5 factorial, divide that into 20 factorial, and notice we get the exact same pretty large answer as we did for the first way. So just as a way to also look at something like example 11, where you partitioned the team into the 5 different positions and looked at how many players you had available for each of those 5 positions in this case. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.